In this video, I will review the logarithmic functions, and I'm going to do that by following this plan that we developed in one of the previous videos called Precalculus Review. That is, first, I'm going to discuss the prerequisite skills for logarithmic functions, and then I will provide some details, or rather summaries, for each of these prompts. And if you need to remind yourself what is all of this about, please watch the video called Pre-Calculus Review. And let's get started with the discussion of the prerequisites of logarithmic functions. And naturally, the prerequisite for logarithmic functions is logarithmic operation. So you have to be able to evaluate logarithms for all bases and all inputs. And in addition to that, you have to know the properties of logs. And there are exactly, I think it is shown 9 of them over here. And you should be able to recite most of them without too much of an effort. And again, let me remind you that there is a natural transition from logarithmic operation to logarithmic function. And in the middle there are logarithmic expressions, and you should be able to identify logarithmic expressions and know how to simplify them. And then there are logarithmic equations, which you also should know how to solve. And logarithmic equations may look like this, or anything that look like this is what we call logarithmic equation, or anything that can be written in this form. And the way we solve this logarithmic equation is by using the definition of a logarithm and rewriting this equation from its logarithmic form in exponential form. So notice how we swapping here the components by producing a whole new statement, but this statement now has the variable by itself. It's not wrapped inside of another operation, and therefore we can actually solve this equation. So if you ever need to solve something like this, then it requires multiple steps. First we isolate log, then we use the property of logarithm, or rather the definition, and then we isolate x. So one way or another, you should be able to solve a logarithmic equation. Now, now that we have discussed all the prerequisites, let's start talking about logarithmic functions. And the first thing we're going to talk about is the form in which a logarithmic function can be written in. And this is the general form. And if you set all the coefficients like c and d equal to 0 and a equal to 1, then you end up with the simplest logarithmic function that looks like this. The graph of a logarithmic function depends on the base. If base is positive, then this is what it looks like. You can graph a simple logarithmic function by using inputs, outputs, put them in a table and graph it by points. Similarly, you can graph a simple logarithmic function with the base that is between 0 and 1. And notice the difference in shapes, well, similarities and differences. The differences are obvious because it's not the same graph, but the similarities are the following. Both graphs have a vertical asymptote coinciding with the y-axis, and both graphs have the x-intercept at 1, 0. So that's an interesting observation. Now, in general, you can graph logarithmic functions using linear transformations and applying them to the parent, to the graph of a parent function. However, you will never have to apply horizontal compression or stretch to a logarithmic function because of the properties of logarithms. Logarithm of a number times x can be rewritten as a sum of two logs. So for example, instead of graphing this function, we can take out this 2 and it comes out as a logarithm, and honestly, I would probably prefer graphing this one than this one. But the point here is actually that in reality, you don't need to know how to graph all logarithmic functions. You just need to learn how to graph one, and then you can easily convert all others to that one. Which logarithmic function you prefer that one function to be. It could be a common log or natural log. That's really up to you, but this is what this property is meant to demonstrate. Now, to summarize graphing, to graph a logarithmic function given to you in this form, you plot the parent function with the properties that we identified earlier, and then you stretch and compress it and shift it according to these coefficients. And lastly, you apply the horizontal shift and move the vertical asymptote along with it. Now, here are some examples of graphs of different logarithmic functions depending on the values of a, b, c, and d. Here, mainly we're interested in observing, keeping track of a and b. So when a is positive and b is greater than 1, this is what we get. When a is positive and b is between 0 and 1, this is what we get. When a is negative and b is between 0 and 1, this is what we get. Kind of looks like this one, right? So there's got to be some sort of relation between them two. And of course, that relation is the result of applying properties of logarithms. And this is what we get when a is negative and b is greater than 1. So these are the graphs of basic logarithmic functions and some of their linear transformations. Now, if you have a graph, you should be able to easily identify the domain and range. Domain of a logarithmic function depends on what's inside of the logarithm. According to the restrictions on the operation of logarithm, what's inside cannot be, it has to be greater than 0. So that creates the constraint. So to find the domain, we just solve the inequality by setting what's inside of the log greater than 0. So in this case, this is the domain, but if it's flipped, if it's c minus x, then the domain will be from negative infinity to c. The range of any logarithmic function is all real numbers, as you can tell, regardless of the combination of a and b. It does go from all the way at the bottom to all the way at the top. Now let's talk about intercepts. To find the intercepts, there's nothing new. To find the y-intercept, you plug in 0 into the function and evaluate it. And note that the y-intercept only exists if c is negative, because otherwise you're going to end up with a negative input for the log, and that cannot be computed. The x-intercepts are obtained by solving a logarithmic equation. Again, I do have a summary here, but the goal is not to memorize it, but to just understand the relation between the question and the skill required to answer that question. Again, note that the y-intercept may not exist, but x-intercept always exists. So logarithmic functions always cross the x-axis. That's an easy observation. All right, asymptotes. We did observe that logarithmic functions have a horizontal asymptote at x equals c. So at the border, at the end of the domain, like for example, unlike radical function, this function has an asymptote. Radical function reaches the end of the domain and stops. It has like a point where it ends. Logarithmic function doesn't stop, it just keeps going to either positive or negative infinity. However, in their domain, logarithmic functions are continuous. So they don't break, they just kind of continue moving indefinitely. Now, in regards to monotonicity, we can make a claim that logarithmic functions are monotone, meaning that they always either increase or decrease. So depending on the combination of values a and b, that's all it depends on. Your function will either always be decreasing, as in these two cases, or will always be increasing, as in these two cases. Now, since it is monotone, it is one-to-one by definition. And if it is one-to-one, Actually, hold on. If it's monotone and continuous, it has to be 1-to-1. Just monotone, it may have a discontinuity in the middle and then cross over. So it's not that it is 1-to-1 because it's monotone, but because it's monotone and continuous, it is 1-to-1. So and because it is 1-to-1, it has an inverse, and you have to be able to find the inverse following this procedure. And here I have an example, but again, depending on whether it's x minus c or c minus x, sometimes you can have kx minus c here. So the point is you just have to be able to solve this equation for y and isolate y here and produce the inverse function. Just like logarithmic functions are inverses of exponential functions are inverses of logarithmic functions. So they are related. Now, just like exponential functions, logarithmic functions are not symmetric in any way. So no symmetry at all. Some of the special features of logarithmic functions would be kind of the opposite of what we consider to be the special feature of exponential function, which is rapid growth. Logarithmic functions are known for their slow growth. If they were to grow slower, so again, take a look at this function. It's barely growing, and if it were to grow any slower, I wouldn't sit here and wait until this function gets to number 15, for example, because it's going to take forever. So we can call that a special feature of logarithmic functions. It grows incredibly slow. Now, in terms of finding equations of logarithmic functions, we were never really interested in that because, well, despite our best efforts, we're still not super comfortable with logarithms, let's put it that way. But because of the tight connection between logarithmic functions and exponential functions, we are definitely more comfortable with exponential functions. And because one can be easily converted to another one, if I ever need to find logarithmic function, sometimes it could be just easier for me to find the exponential inverse function and then from that derive the logarithmic function. So again, you probably never have seen a problem asking you to find the equation of a logarithmic function, but conceptually, theoretically, it could be a question, and to answer it, you would use the rule of thumb. That is, for an equation with 3 parameters, you would need to have at least 3 points, or 3 points will be sufficient. Now, what are some applications of logarithmic functions? And just like radical functions kind of serve the polynomial functions, logarithmic functions serve exponential functions. And from that point of view, they're mainly relevant in the context of some exponential function and their application. But luckily, there are tons of applications for exponential functions. So you definitely need to be comfortable with, if not logarithmic functions, but at least logarithmic expressions, equations, and logarithm as an operation. This concludes the review of logarithmic functions. The purpose of it wasn't to give you all the details and teach you everything. The purpose was to just brush up your memory and guide you in the right direction. But if you need any help or have any questions about any of the slides, please let me know in the comments.